Thank you very much for the nice presentation and for the invitation. It's really a pleasure to me for being here and being able to share with you works, a little bit of my past work, let's say. I will start with some like in my comfort zone, and then I will try to land in this new area. Well, of course, then we try to also to apply like modeling as you was saying. So thank you very much. And yes, this work is a collaboration with Paolo Dodorico from Berkeley University and Chengyi Tu, that was my former PhD and is now postdoc with Paolo. And so this is really a work done with them. Okay, so just a very short presentation on where I come from. So I'm copying the LIPh lab, Laboratory of Interdisciplinary Physics, and as already introduced, we work with complex system, in particular living system, and our main topic, I would say, is ecological system. But in the last years, we also moved with a little bit of with the neuroscience, so brain networks. That is probably one of the most complex system in the world, in the universe, actually, and also environmental science sustainability from this particular point of view of let's say of the world as a complex interconnected system, and in particular food trade, virtual waters, and now I will present this new say block in this part, in this topic of our research. Okay, so first of all, I will be like with the risk of maybe be too basic, but I give an overview of the main concept that I will use. So first of all, okay, we all know about common pool resources. So common pool resources are technically defined as a resource that are owned and managed by community or by actually all the people as a common property system. And these resources are nevertheless both non-excludable, so their use cannot be easily regulated by limiting or restricting access, and also subtractable, so the use of one actors remove resources to other actors, okay? And of course, we have many examples of such common pool resources that are basically the fuel of many activities, and at the same time are also pool of biodiversity, like we think about the ocean. Okay, so one major problem is that, in particular for these common pool resources, we observe an unsustainable use of such resources. This is an example of Paolo that worked also in the Kalahari Desert, and actually he studied that the desertification of such area was basically due to overgrazing of cattle. And in fact, if you protect, let's say, and you try to restrict the grazing, you can observe that there are it may actually regenerate some part of the desert with vegetation. So this is really a classical example. In fact, exactly from this example of the overgrazing, there is the first work proposing the so-called tragedy of the commons was actually from Professor Lloyd in 1832, so very far ago, where he actually exactly making the example of the possibility that in a common field, actors, in order to get more reward, add cows in this field up to a level that leads to the extinction, basically the desertification, and so the loss of the common pool resources. And especially thanks to Garrett Hardin that published in the 60s, a science paper that it became really a seminal work in economics, and not only in economics, it has a 50,000 citation. Coined this term tragedy of the commons that basically can be formulated as an economic problem in which every individual has an incentive to consume resource, but at the expense of other individuals. So this is the non-excludable nature of the common pool. With initially, it was formulated by asking what happened, as I stated by Lloyd, if every shepherd acting on their own self-interest allowed their flock to graze on the common field, and if everybody does act in their apparent own best interest, that's the point. One try to maximize his own reward, but it results in harmful overconsumption. So the grass is eaten to the detriment of everyone. Okay, so this is the tragedy of the commons. Okay. So of course there is a huge literature in economics that I'm not actually expert, and there is really many field of work. So of course I will tackle this problem in a particular specific manner. In terms of a quantitative modeling framework for the tragedy of a common, like many other economic problem, the framework is through a game theoretical approach. And we can understand this tragedy in terms of the most famous, I would say, prisoner dilemma, that for the sake of clearness, I will just briefly review. So there are two players. So let's put ourselves instead of in terms of the prisoners, we are now speaking about fishermen, for example. Okay, so each fisherman have to decide. They both fish on the same lake, and they have decide if to cooperate. Cooperate means that, for example, they cannot fish more than a given amount every day, but there is no way that they one control the other. So everyone is actually free to decide if cooperate or defect, and so overfish basically. And of course, in the table that I'm showing is the so-called the payoff table. And what you see is that if player one, that is represented by the first row, cooperate, so the first player cooperate, and what is the best strategy for the second player? Well, if the first player cooperated, the second player cooperated would get a reward of 3. If he defected, he would get a reward of 5. Okay, so is the best interest. At the same time, if player one defect, the second player would get a reward of 2 if cooperate, and a reward of 2 if defect. So in any case, for player 2, it's better to defect. So it's called the dominant strategy. Okay, so the player 2, regardless of the strategy of the player 1, decides to defect, and this is symmetric. And so the equilibria, the Nash equilibria of this game, is both defectors. But you see the paradox here that the equilibrium, defectors, has a reward of 2, but actually the equilibrium cooperator would have higher reward. But basically it's not stable, it's not accessible, this equilibria, if each player wants to maximize its own payoff. This is a version of the prisoner dilemma, and just to give a quantitative overview in terms of modeling. Okay, this kind of game can be modeled through the replicator dynamics, where X represents the strategy, the fraction of cooperators in the system, for example. And this equation is very simple. It's just saying that what you do, you compare basically your payoff with the other player payoff, and you just tend to copy the most profitable strategy. Okay, so every time step one tends to copy the most profitable strategy. This is just an equation describing such evolution of the strategy. Okay, so we have this is a well-established theoretical framework to study, and in this case example, you can see a, let's say, two-player tragedy of the common example. Okay. Now, this common pool tragedy of the common is actually, and unfortunately, quite real fact. In fact, I just want to make an example, but there are many examples of this. For example, the Grand Banks that are region of the Atlantic Ocean near Canada, as you can see in the pictures, the Grand Banks are fishing grounds of the coast of the Newfoundland. And for centuries, explorers and fishermen described the region as a home to an endless supply of cod fish. And in the 60s and the 70s, advances in fishing technology allowed for huge catches of cod. Following a few dramatically large seasons, you can see this in the peak here in the picture, the fish population suddenly dropped, forcing Canadian fishermen to sail farther to maintain the catch size each season. And in the early 19, you can see in 1992 precisely, cod population was so low that the Grand Banks fishing industry collapsed. And it was too late for regulation and management, and the coast stops has been irreparably damaged. So you can see, in fact, that they never recovered. Since then, the cod population have remained low, and some scientists doubt that Grand Bank ecosystem will ever recover. Okay, so this is an example of tragedy of the commons. This is not the only one. Okay, and in fact, there are many cases in which we observe such over-exploitation of common pool resources in different terms and from different point of view. But the bottom line is that the problem of sustainability is strictly linked to the problem of how to regulate such common pool resources. Okay, from this point of view, we can distinguish the problem in terms of spatial scale, let's say. So, of course, there are global environmental issues. So just for example, pollution is another case, an example of common. Okay, so the environment, our air is a common resource, and of course, we can because of the pollution degrade this the quality of our air, for example. And as this is an example, but there are many global environmental issues. Climate change is the most pressuring one, probably. That, of course, needs global environmental governance. And at the other scale, so the individual local scale, we have community scale governance, so small communities that has to regulate. You can think also like a university or very community level where they needs to regulate and decide how to use and common pool resources in locally, no? And of course, you can think about some regulations, some bottom top-down regulations, so from the global one that reach the bottom, the smaller scale, or vice versa, try to understand and see good example of community scale governance and try to upscale such rules. Okay, so in general, the tragedy of the commons has pushes the regulatory process mechanism and organization to think in a top-down matter, so to centralize control. Because of the prediction that of the tragedy of the commons, many open access resources have indeed resulted in tragic levels of overuse and sometimes destruction, as I already described. And so many analysts and have relied upon need for centralized control. But unfortunately, the result of many of these efforts have been the opposite of what was hoped, and evidence has now been amassed. The central regulation has frequently accelerated resource deterioration and complicated by several problems of corruption and inefficiency. And so this kind of centralized control has shown very strong limitation, because sometimes are the government themselves that somehow pushes this kind of over-exploitation of resources. And one of the problem that also my collaborators Paolo Dorido study a lot is the so-called land grabbing. So like countries that go in other countries to buy land and to use that land to produce or to exploit the land in other country, basically. But of course, for example, deforestation is another incredible and important problem about that. So, well, a very important voice that somehow put a new light in such a problem is Ellen Ostrom, that she was a Nobel Prize in 2009 and she passed away in 2012. And she wrote this important book, Governing the Commons, but many also scientific papers on this topic. And she basically claimed that many scholars who draws on traditional conception of the markets and the state have not recognized that there are some kind of self-organization that is a potentially viable form of organization that have either called for their removal or ignored their existence. In other terms, she studied many cases of community that has found a kind of self-organized regulation, and that was very efficient in the maintenance of the common pools. And the main force and the main push basically of such success was shared goals by individuals. So having shared goals by individual of the community was pushing the community in a sustainable use of such resources. And this kind of result have been also shown in quantitative terms by the National Research Council, that in 2002 provided reports and showing that there were many non-state provision units that were able to successfully govern their commons. So she called basically for a research that was looking in such self-organized mechanism for governing such common pool resources. And so the idea is basically that we start from community scale governance and then we move up. We try to understand the main ingredients, elucidating the main mechanism, and then try to understand how to implement it in a larger and larger scale. Okay, I think that one example of such kind of experiment, a very nice experiment about how to incentivize or understand the mechanism that allow for sustainable use of resources is this work by Martin Nova Group in 2014, Cooperating with the Future. And basically they make a very neat experiment where they basically have different group of players, and each group of players, each individual could decide if using the resource that was a constant number of item to take just the sustainable amount of item, or taking more item than what the resource is sustainable. And after the first group has all exploited, all extracted resources, then a new group enters. And of course, the reward was proportional to the amount of extraction that each individual made. Then a second group of people enters. And if the first group, you can see here in the plot, if the first group, like in the green case, used a resource, but leaving high enough amount of resources, so above the threshold T, so that the resource naturally regrow to its capacity, then the second group would find the resource there. So they have to decide how much resource to take. If they extract an amount of sustainable resource, then the resource do not pass the critical threshold, it regenerates, and so on. And so, for example, in the green case, you can see that all the fourth generation have used successfully the resource um, without problems. But on the other hand, it could happen that the first group take too much resources, so it go below the threshold T, and in this case, there is no regrowth of resources, and therefore leaving empty all successful generation. So what this work have shown is that in an unregulated, completely unregulated scenarios, there was no way to sustain the resources for future generations. Okay, so the first group was basically taking everything, but through a mechanism of voting and basically deciding and excluding potential defector from the community, they found that there was a very high sustained continued pools of resources, I can say here in the graph, independently of the discount factor, that is how the resources decreases its quality generation by generation, or even the threshold level of usage, of critical usage. So they propose as a mechanism, basically of shared goals, the voting, so democratic decision about the use of resources. So once this of course, this was in order to have sustainability of the resources. The result of the vote was obliged all the players to follow strictly that kind of strategy. Okay, there are many issues here, but the 2 points that I want to make here is that the first is that there is no resource dynamics. So the dynamics of the resources is basically very synthetic. It's just like a 1-0 dynamics, and also that this kind of experiment are difficult and time consuming to obtain, and very limited in terms of amount of data that one can actually obtain. So let's first focus on the resource dynamics. So I will go quite fast here, so because I spend more time than I was expecting for the first part. So just want to, so the point here is that in the literature there was no much modeling of the resource, and actually this is instead somehow my background. So I really try to model complex behavior of resources in time, and also used by multiple players. And that's so the first part is just to show you that we have like a modeling framework where we can try to describe even in quite complex scenarios how the resource change in time. Okay, so for example here we want to understand if a resource is sustainable, but we have many users that may interact, okay, and possibly also many resources. Okay, so each resource, each user, for example, each country has its own resource, but one country can use multiple resources. Okay, so basically this work it's just published in 2019, and the idea here is to find a mathematical framework to describe such complex scenarios. So I just mentioned some mathematical details for the sake of those who are interested in a more quantitative framework, but it's not really fundamental. So just to say that this is an equation that describes the evolution of the resources, and here there is the consumption of the resources by users, the growth, the natural growth in the absence of harvest, some ecological mechanism typically observed in ecological resource dynamics, like the so-called LIPh effect. And then we have the second part that is basically the resource outflow, the extracted resources. And here we can also consider, for example, input of resources, okay? So we have both input and output of resources that goes in the balance of that determine the evolution of such resource dynamics. Okay, this is a quite complex equations, because you see this is a there are many resources, many players, and so this is actually it's a multidimensional system of differential equations, and typically these are difficult to study numerically. So one have to do a lot of simulation, and you never know the sensitivity. So it's a kind of problematic, but luckily there are some kind of approaches from physics where we can try to simplify the system, but without losing too much information. Okay. And so the bottom line is that from a system that is kind of unpredictable in n dimension, we can obtain like a very simple one-dimensional equation that we can study, and for which we can basically understand, and this is you see now it's just one single equation that describes basically the average of all resources. Okay, it's a weighted average that can be obtained, and the point here is that we have now one equation that describes the dynamics, the evolution of the resources. And in this one dimension, we have many techniques to study this transition from sustainable or unsustainable, because these are two equilibria. And so basically we can have like a transition between two equilibria. And we show and we play with also synthetic networks and try to see how this kind of sustainability is related to the network. And we see that the main point is that this parameter we call the heterogeneity of the network, that is how asymmetric is the network. So in a minute, I think it will be more clear. And so just to mention that in this context, we can actually have some quantitative analytical understanding of the problem. And you can see in the bottom, in the panel C, that what we can do is to, for example, see the effect of the globalization, that is how dense is the network of extraction of resources. The connectivity, the larger is the connectivity, the more dense is such networks. And we can see that basically we can study the probability of sustainability of the resources based on such parameter, that is the connectivity. But this graph, for example, in this setting where you are using completely random graph, the higher is the connectivity, the more sustainable is the system. But if we change the structure with a more realistic structure, for example, the so-called scale-free networks, then you can see in the panel D, the things completely change, and for very high connectivity, we have that the probability to be sustainable is very low. Okay, so this is just an example in which we can study the sustainability of the dynamics based on some parameters. Here is order parameter, control parameter, here is the connectivity, and study how the sustainability of the resource depends, in this case, with globalization, that is the connectivity. And then we also apply this to real data, studying the full thread networks. And indeed, we show that by fitting our model parameters on such data, we can, of course, qualitatively, in this sense, it's not some quantitative description in terms of, it's a very simplified description of the system, and yet we can see that the time, like in the last years, globalization, you can see here the connectivity in time, you see these positive trends means that the globalization increase in the last years, of course, and this had an effect of destabilization of our resources. So we are closer to kind of transition where the system will not be sustainable anymore. Okay, and the main reason of this, what we think is that we have a lot of asymmetries in the exchange of resources. So we have countries that deeply depend on other countries in terms of their sustainability. So we have very big exporters and very important importers of resources. And this, of course, reflects the uneven distribution of natural resources. Okay, but not only that, because of course, for example, if you think about oceans or fishes, these are common pool resources, but there are of course countries that use more common pool resources than other. Okay. Okay, so this was maybe too quick, but I was just wanted to give you the fact that it's important to model the resource dynamics. We cannot think about the resources just as a 0-1 variable, let's say, okay, as is typically done in game theoretical frameworks. So the new part was now merging these two aspects, so the game theoretical frameworks with the resource dynamic, and try to set up an online platform that was performing these kind of games. Okay, so in this setting, first of all, we need to introduce these games with environmental feedback that while we were working, this published paper in 2020 came out. Okay, so just with the theoretical part, just to see that this is very new topic. So basically here we have the players like fishermen, in our case, they may be connected so they can know what the other is doing, and they fish and they have to decide how much to fish. Okay, and then there is also a non-trivial resource dynamics. So for example, the number of fishes in the lake we are considering, that is, they follow, for example, a logistic growth that is a kind of very simplified but kind of realistic growth of fishes. Okay, and so now what you can see here is that the resource depends, of course, on the strategy of the player, because the resource depends if the player cooperate or defect. At the same time, the strategy depends on the resource, because if I have to decide, of course, my reward will depends on the amount of resource that they can extract. Okay, so for example, if the resource goes to 0, I cannot extract anymore, so I will not have any payoff. Okay. So what is here is the simple replicator dynamics. So this is the one that I showed before. So this is the classic framework to study such dynamics of cooperator. So the idea is that one player has to decide if extract more resources than what is sustainable. So for example, you extract with a rate ED that is greater than the natural resource growth that is T, or cooperating, extracting with EC. Okay. And so in this case, what the player has to decide if he wants to maximize its own payoff, right? So this is what game theory tells us. I want to maximize my reward. So what I do, I look at the average reward of the other player depending on their strategy, and I choose my own strategies. But theoretically, in this setting, we still retrieve the tragedy of the commons. Okay, so there is no way to avoid the tragedy of the commons, even in this setting. If each time step I want to maximize my payoff, then comparing to the other, then there is no other strategies than defecting. Okay, so we want to test this on data. So this is the point. So it's very difficult to obtain data of common pool resources combined with strategies. And that's why we thought, okay, actually inspired by the work of behavioral machine that I was reading in that period, we say, why don't we do something like that? Like, why don't we play like a game? We build a game where players can actually play, and then we can kind of collect data about such game, no? And so we can start to have many data, and for example, also observing if we found some difference depending on the geographical or cultural things. Okay, so this is the ongoing work, so it's not finished. Everything I'm showing here is it's basically unpublished and ongoing, but I want to try to share with you the main the result that we obtained for now, like 5 minutes. And so first of all, how the game is settled. So the experimental setup is the following. So each player has to decide, as I already explained, if they want to cooperate or defect. Okay. Of course, here there is no equation for X because it's the player that decide what to do. Okay. We cannot control the strategy. What we can control is the dynamic of the resource underlying the decision based on the decision of the player. Okay, so the decision of the player will have an effect on the evolution of the resources. So if we focus, for example, in the case A, we can see in the continuous line the resource. Here we start with 50% cooperators, 50% defectors. Then each player, I will show you in a moment which are the information that the player have available. for example, here, start one change strategy start to defect, and at a certain point, all players start to defect. And what you can see is that the resources slowly goes to extinction. While in this other case, there is a convergence, a consensus to cooperation. And what happens is that the resource, of course, decreases because players are using resources, but remain sustainable. Okay. So this is basically the game. Each player, every time step, must decide based on the information that I will show you in a moment, what to do, if to cooperate or to defect. Then they will see the result on the resources after their action. They don't know before, of course. They know the current state of the resources. They decide what to do, and then the resource is updated, and they discover what is the following amount of resources available in the next time step. We play two games. One where each player playing on his own, and the reward is proportional to the total player extraction of resources. So at the end of the game, how much you have extracted, proportionally you will be paid. In the game 2, the reward is still proportional to player, but we divide all players in two groups, and only the group with the total overall extraction payoff will be paid. Okay, so we induce some shared goals without do nothing. We just say, okay, only the group that is able to extract more during all the time of the game, and they don't know if the game is short or if the game is long. They don't know. Okay, they have to decide how to let's say manage this. But the point is that each one is still paid in its own proportional to its own extraction, but only the group that has the overall cumulative in time total resource extraction will be paid. Okay, is clear this?
If I could just ask a question, like,
yeah.
So basically in game 2, you've introduced sort of two things.
Yeah.
There's both. This is basically a group selection dynamic, right? Like you need to cooperate within group and compete across groups in order to succeed.
Yeah, so it's not obvious that you need to cooperate, in the sense that if, for example, cooperating, you obtain less resources than the other group, you will not be paid. So you cooperate if you think that cooperation is in the long term. So what we are pushing here, the players, is to think not only at every instant, but we are pushing them to think about all the game duration. Okay, this is what somehow we are inducing in the second game. Okay, so this is the setting. So this is the what players see. So you have, of course, the cooperation of the faction button. There is an underlying network of players that you don't know. Okay, and we change this in the game. We do fully connected, Barabasi, and so we can change how the players are connected. And you can see your cumulative payoff, that is the payoff summed over all time step. You can see your instantaneous payoff, so how much of reward I'm getting if I'm doing a cooperation or the factor. Then I can see what happened to a random neighbor. Okay. And finally, I can see the available resource volume and the cooperation ratio, the overall cooperation ratio. Of course, these are information that we have decided to show in this kind of game, but we can change, we can add, we can remove, of course. This is a very fluid kind of setting. Okay, but the experiment that we have done up to now show this kind of information. Okay, so we played the game up to now in two different settings. One is in Yunnan University in China, where basically we give the link to this game to a set of students. Okay, it's around 80 students that play the game. 40 play the game in game type 1, and the other 40 play the game in the second setting, game type 2. And then we play the same game in Berkeley. Again, calling the students, giving them a link. And for each of these experiments, we have several replicas. And the idea is that this kind of games will be available also in a standalone version, where we learn from previous game strategies, we implement it, and one can play alone, like without the need of organizing group. And also we will have a kind of dynamic playing that is less boring. This is an example. So where you can actually move and game play like in a more fun way, because one of the problems is that the game is quite boring. Okay, so let's see now, and I'm going toward the conclusion of this result. But before showing the result of the experiment, this is related to IAD questions. I want to make this point very important clearly, because this is really what we theoretically also introduce as a novelty in our approach. So this is the classic, as I said, game with replicator equation. If I look at the instantaneous payoff every time step, you can see that independently of the number of cooperators in the system, the payoff in a given time step, independently of the resource, for the factors, is always higher than cooperators. Okay? So in other words, this equation 2 will go, okay, towards 0. Okay? And so there will be no cooperators in the long term, because the payoff is always higher for payoff for the factors. And then this R in this part, it will be, so this part, you see, this is the cooperators. These are the part of the defectors, but X will go to 0. So this part is simply become EDR, and this goes to 0. So we can solve this problem analytically, and there is no way to have sustainability. But if you now think about the cumulative payoff, that is the integral over the time, then the situation becomes much more complex. Okay, so this is a very specific case where we can compute everything analytically. So where X star is fixed, so it's an amount of cooperators. In this case, we fixed. In this case, we can compute analytically. You can see that depending on the duration of the time, it may be convenient to defect, or maybe it may be convenient to cooperate. So in terms of cumulative payoff, defectors is not the optimal strategy in any setting. Okay. So what we have introduced is an optimal control framework to understand and describe the result that I will show of the experiment, where I added that this parameter W that is called the selective parameters, and typically this is positive because we have positive selection, of course. But now this W follow an optimal control problem, it's called like this, that is, we want to maximize the overall payoff in time, okay? And of course, this result will depend on the duration of the game. So you can see here in panel A, if the duration of the game is quite small, then resource goes to 0 and cooperators tends to go to 0. While if the resource, if the game is very long, it's quite long, it's not very long actually, then what happens is that cooperators goes to 1 and the resource is sustainable. So theoretically, this framework show you that if we think about cumulative payoff, we can have sustainability. Okay, so this is the result of type 1 game in China. So here, every player just play on its own. There is no shared goals. What we found is that in all realization, resources tends to 0 because the majority of the players defect. So we have a quick convergence to defection, So here 80% of the player defect, just 20% of the player cooperate. The red line are the different realization. And in all the cases, the cooperation is not enough to sustain the resources, so we have the tragedy of the commons. Okay, and this is how this control parameter behave. And you can see that the black line is what the fit of our model on such data. Okay, so we can see that using this optimal control framework, we can describe basically the behavior. And the idea is basically that the player act as the game is very short. While in game shape, in type 2 game, always in China, things completely change. And what we found is that the cooperators quickly, in 9-time step, converge towards 80%. Okay, of course, there are fluctuations depending on realization, but there is a quick convergence. Oh, no, not so quick, because you see the convergence to defection was very, very quick. Sorry, was very, very quick here to defection. Here we have that in 10-time step, all players start 80% of the player cooperate, and this is enough to have sustainability of the resources. And so we have a self-organized sustainability induced by such shared goals. Okay, but at the same time, very interestingly, in Berkeley we didn't find the same thing. Okay, so this is an ongoing result. What we actually found in Berkeley is that no matter of the game, players always tends to quick convergence of a good fraction of cooperators. So 50% with high variability in the type 1 game, so there is no shared goals here, and yet 50% of the player cooperate, and 60% in the type 2. So there is a very small change in cooperation that is already high in the first game. And in both cases, we have a relatively small but sustainable resources. So the resource does not hit zero in both of the cases. Okay, so this is now we want to replicate again another game in Berkeley, but this opened the question: is this because, like, culturally, like, students in California have more sensitive to maybe sustainability issues than, for example, other countries, or there is some kind of, so these are open questions that we are now trying to understand. Okay, another interesting part is the network structure. We change, as I mentioned, we can change how the players see each other, and we basically found that although not strong, the structure lead to a slightly higher number of defector in game type 1, and a slightly number of highly number of cooperators in game type 2. So it seems that the structure of the network, the heterogeneity of the structure of the network, reinforce what typically happen without structure. Okay, so this is also ongoing a kind of result. We are replicating and also simulating results in a simulating environment. Okay, so this is the kind of data that we can obtain from the systemic sustainability game. We can think about many variants. We can think about early warning of messages during the game. So we can really think about many different, let's say, variants of such a game with environmental feedback. And the idea is that this can be used to collect more and more data in the next months. So concluding, we have developed a sustainability game that runs on an online platform, and it can be used to implement a set of experiments simulating decision of viewers harvesting common pool resources. And if all agents play against each other with individual goal, then they will tend to maximize the individual instantaneous payoff. And we see that in most of the cases, we found that indeed the strategy of the commons is retrieved. But this is not always so. In fact, we found that self-organized sustainability is possible, especially in the presence of shared goals, as predicted by Ostrom framework. So we also propose this quantitative modeling based on optimal control theory that elucidate the mechanism behind such emergence of cooperation, that is the maximization of long-term cumulative payoff of the players. And so we think that this idea of collective payoff can allow a majority of prosocial individuals to override a poorly selfish minority, and so indeed to help the cooperation and sustainability of future generations. Okay, of course, this is what we hope for our future. Thank you very much for the attention. I hope I probably went a little bit too far. Sorry for the delay, and thank you very much.